The next two topics trace the construction of the number systems, and through them, I want to introduce the concepts of monoids, groups, rings, and fields. Let's begin with natural numbers. We saw this set before. We simply start with 0 and then we keep adding 1. So the elements of the set natural numbers are 0, 1, 2, and so on. Humans invented natural numbers to count, and for counting alone, they are perfectly sufficient. The natural numbers themselves rest on an axiomatic foundation that makes the notion of counting precise and free of ambiguity. We will not go into it in this set of videos, but if you're curious, the right place to start is Peano's axioms, which are 5 simple rules stated by Giuseppe Peano in 1889 that pin down exactly what natural numbers are and why induction works. We will meanwhile focus on count addition as an operation over natural numbers. So if you look at addition and then you have three important properties you can sort of abstract out. If you take two natural numbers, then if you add them, it will always yield another natural number. So this is the first property that we are looking at. The second property is that the addition operation is associative. We have covered what associativity means in one of our early videos. Specifically in this context, it just means that the bracket here is not important in this expression. So you could add a plus b first and then add c to it, which is equal to adding b plus c first and then adding a to it. And this holds for any three natural numbers a, b, c. Finally, there is a special element 0 called the identity element, such that if you take any natural number a and add 0 to it, you get it back. So what mathematicians observed is that there is nothing specific about natural numbers here. They could identify many sets with a binary operation. What we mean by a binary operation is that you could sort of take two natural numbers and operate on them and yield another natural number. So we'll see the definition of a binary operation in more general very soon. But what they identified is that they could see many sets with a binary operation defined on them that satisfy these three properties, and hence it made sense to abstractly state and study them. Such sets with a binary operation defined on them, which satisfy the three properties we just discussed, are called monoids. Let us first see what a binary operation is formally. If this formalization feels alien to you, then it is okay. It was the same for me initially. You can revisit the definition when you see more examples and really grasp why a binary operation is defined the way it is. The idea is to first understand what intuitively a binary operation wants to achieve. Remember, we are abstracting out properties from the example of natural numbers. A binary operation here is associating a pair of natural numbers with another natural number. Since we want to abstract out a definition, let us first get rid of natural numbers and look at an arbitrary set S. So we have two elements, A and B, in S, and two tuples, A comma B and B comma A. Remember, tuples belong to the Cartesian product of S with itself, that is the set S cross S, and A comma B, the tuple A comma B is not equal to the tuple B comma A. Now you have two options. Associate the same element C with the tuple A comma B and the tuple B comma A. This could be done as we saw in natural numbers. If we write 3 plus 5 or 5 plus 3, the result is equal to 8. In particular, we are associating 8 with the same tuple 3 comma 5 and 5 comma 3. But many operations we encounter actually exhibit the property that these results are different. That is, when A is operated with B and B is operated with A, we get different results. For example, if you have ever multiplied two matrices, let's use capital A and capital B to denote these matrices. Then in general, multiplying A with B, that is the product of matrices A times B, is different from multiplying the matrix B with A. So In particular, A times B is not equal to B times A when you consider matrix multiplication. Hence, for a general definition, we want to map these two distinct tuples A comma B in the example that we are looking at. So the tuples are A comma B and B comma A. So we want to map these two distinct tuples to different elements. So we write a binary operation as a map from S cross S to S. In particular, the domain of the map is the Cartesian product of S with itself, and the codomain is also S. The map associates every ordered tuple from the Cartesian product S cross S to elements in S. Since the domain consists of ordered tuples, observe that the image of A comma B, the tuple A comma B, is different from the image of the tuple B comma A. For specifically a binary operation, we introduce a shorthand notation, which is a convention in map. So if the image of A comma B is C, that is the tuple A comma B maps to C under the binary operation star, then we write A star B is equal to C. Typically, in modern textbooks, this property, that is a binary operation, is referred to as the closure property. But my view is that it helps in just remembering this property as a binary operation. Another convention is how we resolve expressions involving multiple operands. For example, suppose you encounter A star B star C. This is really composition of map corresponding to the binary operation star. That is, it is equal to, you can write it as star the input A comma B tuple. So the operation between A and B, and then the result is again operated with C. So it's just function composition where inputs are tuples. So this is essentially equivalent to resolving Y as the result of A star B and then using that to operate with C. Observe that we could have started from the right, that is first resolve B star C as Y prime. So Y prime is equal to B star C, and then used Y prime to resolve A star B star C as A star Y prime. In general, these would yield different results. In particular, in general, a binary operation does not satisfy the following, that if you resolve A or B first and then use C to resolve the expression, or you resolve B star C first and then use A to resolve it with the result, they are not equal in general. But in natural numbers, we had this property that we could resolve A plus B plus C from either direction. If a binary operation has this property, then we say it is associative. In particular, it is associativity that ensures we can resolve expressions from any direction. Most interesting objects that we encounter as engineers would have operations that are associative. Finally, the third property we saw is that there is an identity element E in S such that for all A in S, A star E is equal to A as well as E star A is equal to A. Remember that since a binary operation is mapping ordered tuples, it is important to state both A star E as well as E star A is equal to the element itself. This, in the case of natural numbers, follows trivially because natural numbers, as we saw, forms a monoid under addition because it satisfies all the three properties, but it has an additional property that is for all A comma B in natural numbers. So it's not S here. This is natural numbers. So for all A comma B in natural numbers, A plus B is equal to B plus A. That is, when this happens, we say that the binary operation is commutative. In specifically, both the ordered tuples A comma B and B comma A are mapping to the same element, map to the same element. Such monoids where the binary operation is commutative with this additional property that both tuples A comma B and B comma A for any A comma B map to the same element, such monoids are called commutative monoids. Just abstracting properties and boxing them is not sufficient. We have to show that such objects with these properties appear quite frequently and studying them is very important. We will cover interesting examples of monoids, groups, rings, and fields once we build the entire number system. For now, we continue how integers were thought about. At some point in history, mathematicians started asking a different question. What values satisfy a given equation? For example, consider the equation x plus 1 equal to 0. Does there exist some number which, when you add 1 to it, gives 0? In natural numbers, no such number exists. The equation has no solution. Throughout most of human history, this was not a problem. It was simply a meaningless question. You cannot have fewer than 0 things. The equation is absurd. And yet, the moment you try to do serious mathematics, the equation forces itself on you. Algebraic formulas produce terms that demand a sign reversal. The universe does not care that your number system has no room for -1. This is the pattern that drives the entire construction of numbers. An equation exists, it demands a solution. The solution does not exist, so we build a larger world where it does. Then repeat. The underlying primitive is always a polynomial equation. Remember this. We just saw that the equation x plus 1 equal to 0 does not have a solution in natural numbers. What if we demand a solution? The fix is to add inverses. For every natural number a, add its additive inverse minus a to the system. The result is the set of integers that we all know. What is important to understand is that the negative integers are not an invention, they are a demand, forced by the requirement that the equation x plus a equal to 0 must have a solution for any natural number a. This is not a trick specific to integers. It is the fundamental move of modern algebra. When an equation has no solution in your current system, you do not declare the equation meaningless. You build a larger system where the solution must exist and you study what structure that system is forced to carry. Every number system in this series was born this way. So were groups, rings, fields, and vector spaces. Remember, the equation comes first and the algebra follows. It is easy to extend the addition operation to integers. Naturally, integers satisfy the first three properties that natural numbers with addition satisfy. In particular, addition over integers is closed. So if you take two integers and you add them, you will always get another integer. Similarly, the addition operation is associative. We have seen what associativity means. And there is a special element 0 called the identity element, such that if you add any integer a to 0, you get back a. But it has one additional property. You take any integer a, there exists an integer minus a, such that a plus minus a, which is equal to a minus a, will yield you the identity element 0. In particular, minus a is called the inverse of a. So Z with addition satisfies four properties. The binary operation by definition is closed. So it is the addition is a binary operation. It is associative. There is a special element 0 called the identity element, and inverses exist. So mathematicians again box these properties, these four properties, and called a set with a binary operation satisfying these four properties as a group. So when we say it's a binary operation, the first property is implied. Formally, a group is a set S with a binary operation satisfying the following four properties. The first three are the ones that determine a monoid. In particular, a group is a monoid under the same operation with an additional property. For every A in S, there is a B in S such that A star B or B star A. So either way, so remember that binary operations map ordered tuples. So A comma B tuple is different from B comma A tuple. So both A star B and B star A gives you the identity element. B in particular is called the inverse of A. And finally, if it's a bit of notational convention that if the operation is denoted using a plus, then we write the inverse b as minus a, and if it is represented using a multiplication operation, then it is denoted as a inverse. I want to note here that for a group, we could in properties 3 and 4 just write the existence of identity and inverses in one direction. That is, just state that A star E is equal to A and A star B is equal to E, and use them together to show the other directions for both properties. That is, E star A is equal to A and B star A is equal to E. We will not show this here, but this is a good exercise to show this result. We just saw that integers with the addition operation forms a group, but it also has an additional property. So we saw that integers with addition has the four properties of a group that we stated, but it has an additional property where if you take any a comma b, any integers a comma b, and you operate it, that is you do a plus b or b plus a in whichever order, it is the same. So this property where the order is not important while operating on the operand is known as commutativity, and we saw this even when we defined a commutative monoid. So a group where the operation is commutative for any, that is for any a comma b, you do a plus b or b plus a, you get the same value. These groups are called as Abelian groups. It is named in honor of the mathematician Niels Heinrich Abel. Observe that every linear equation of the form a plus x is equal to b is now solvable in integers. And in particular, x equal to b minus a is the solution of this equation. But addition is not the only operation we care about. Multiplication existed long before algebra. It was part of counting from the very start, present in both natural numbers and integers. So let us ask the same structural question, but now for multiplication. Does natural numbers under multiplication form a monoid? So let's try to answer this. If we see natural numbers without the identity element 0 of addition, then it is easy to see that it is indeed a monoid. So if you, it is close. So if you take two natural numbers and you multiply them, a times b always is a natural number. Similarly, the operation is associative, and the identity element is 1. Remember that it is important for the 0 to be not part of this set, to become for it to become a monoid, because the identity element being 1 only makes sense when 0 is not part of this, 0 is excluded from the natural number set. So similarly, we can work out that z under multiplication without the 0 element. So 0 in specifically denotes the identity element of the addition operation. Remember this. So I'm removing the identity element under the addition operation to make it a monoid. So z without 0 element is also a monoid under multiplication operation, but it is not a group. We will see this. So the first answer is yes. This is yes. And this is no. It is yes if it was a monoid. Monoid, so n without 0. Remember, it's without 0, it's a monoid with the identity element being 1. And z without 0 is also a monoid, but it's not a group. The reason integers without 0 under multiplication do not form a group is because the integers do not have inverses under multiplication. So let's see this in more detail, and this will essentially motivate the construction of rational numbers. So if you look at the equation 2x is equal to 1, this does not have a solution in Z. In particular, you cannot put any integer in place of x such that 2 times that integer will become equal to 1. And this essentially means that we need to extend our number system so that we can find a solution to this equation. So we will come to this, but before we proceed, let us observe the two operations on integers that we just saw. One is addition and the other is the multiplication operation. So we saw that integers under addition forms an abelian group. Similarly, the set of integers without 0, where 0 is the additive identity under multiplication, forms a commutative monoid. We also looked at this. So if we observe carefully, these two operations, the addition and the multiplication, they behave very nicely with each other. So if you look at the LHS of this expression, you're performing the multiplication of A with the result of the addition of B and C. And this is actually equal to if you multiply A with B and then add it to the multiplication of A with C. So in particular, this multiplication operation is distributing over the addition. So we say that multiplication distributes over addition. And in particular, this means that these two operations are compatible with each other. So we call such sets with two operations, plus and multiplication. So you have two operations. And when you're looking at the multiplication, you remove the additive identity from the set. And without the additive identity under multiplication, it forms a monoid. And the multiplication distributes over addition. So the sets with these two operations and all these properties are known as rings. Formally, a ring is a set S with two operations, addition and multiplication, such that S under addition is an abelian group. And if you take the identity element of the addition operation, so E is the identity under the addition operation. If you take that element E out of the set S, the set that remains is a monoid under multiplication. Okay, and finally, you want that the multiplication operation distributes over addition. That is, if you take any three elements in S, A, B, C, A times B plus C, so you apply multiplication to the result of the addition of B and C. That should be equal to multiplying A and B, multiplying A and C, and then adding them. So that is what distributivity means here. Then if the set under the two operations plus and multiplication satisfies these three properties, then we say it is a ring. Okay. If additionally, which we saw in the case of integers, if S under multiplication, so when I say S under multiplication, by default, I mean that I'm removing the identity element here. So S without the identity element is a commutative monoid, then we say that it is a commutative ring. Okay, so remember that this is without the identity element. Let me just make a note here. Okay. So S without the identity element, if it is a commutative monoid, then we say that it is a commutative ring. You might ask, why not do a similar thing with natural numbers, where we say natural numbers under addition forms a commutative monoid. And if you remove the additive identity, which is zero, from the set of natural numbers, then under multiplication, this set forms a monoid. And naturally, the multiplication distributes over addition over natural numbers. So, has this structure been abstracted out and studied? Yes, this has been studied, and the structure is called a semi-ring. We will not develop it further here because for everything that follows for us in this set of videos, the ring is the right level of abstraction. But I want to pause and emphasize once more, one of the most important habits in mathematics is showing that a newly defined object is not a curiosity. Once you name a structure, you immediately look for examples of it everywhere, in different number systems, in geometry, in computation, and so on. The wider the zoo of examples that you can create, the more justified would the abstraction be. We have just seen that natural numbers exhibits semi-ring structure with addition and multiplication as the operations. Similarly, the integers under the same operations, the addition and multiplication exhibits ring structure. We will return to this habit of collecting examples once we finish building the entire number tower, that is the set of number systems. So we will look at rational numbers, the construction of rational numbers in the next video. And then eventually we will look at the construction of real numbers and complex numbers. But you will see that rings and fields appear in places you would not expect.